Right. Okay, so what we are discussing then is control theory, right? So control theory is a broad branch of mathematics that help you understand how you can automatically control a system. Okay, so one of the most important parts about control theory is this concept of a system, right? A system. You also call it a plant sometimes, not like a biological plant, but any sort of thing that we ultimately try to control is what we call the system, right? So usually we use block diagrams to kind of denote these things. So for example, I'm just going to call this system, I'm going to represent this system with just a block, right? So a system can be anything. It can be an economic system, it can be a robot, it can be a biological system. It's basically anything which has some sort of input, right, coming into it, and some sort of output going out of it, right? So that's a very broad definition of what a system is. So like I said before, it can be economic, biological, robotics. Obviously in these lessons we are concerned about how it applies to robotics, but always remember the mathematics in control theory really apply for a very broad set of topics. So I think, like, as far as certain engineering subjects go, control theory is super important. And if you have the time, I'd suggest spending more time learning a bit of control theory, because its applications not only fall into robotics but fall into a lot of other wide subjects, including economics, including biology, including physics, everything, right? So this system could be any sort of uh, physical or biological or physical system, right? So as a simple example, let's talk about um, let's talk about having a shower every morning, right? So if we think about that scenario, you going and having a shower in the morning as a system, right? We could kind of describe it in these terms as having an input and an output, right? What I mean by that is, right, imagine you have your shower, right? Um, and your input to the shower will be how much you open your hot water and your cold water taps, right? So this is your shower. What will your output be in this scenario? It will be, say, let's say what you're really mostly concerned in this situation is the temperature of the water coming out, right? Imagine the water, like, you're not worried about the flow, like how much of water that's coming out. Your output that you're worried about is the temperature, right? Which is an important thing to worry about, right? When you're having a shower, if you have it too hot, right, you're going to burn. If you're going to have it too cold, you're going to freeze, right? So you can think of this as a simple system with inputs and outputs, right? And the great thing is, you can take any sort of thing you're interested in, like this, and think of it in terms of an input and an output and a intermediary system in between them, right? And the first step in control theory is kind of modeling this whole scenario mathematically, and we're going to discuss that today, right? But before jumping into that, I'm just going to use this simple example to explain the difference between what we call an open loop system, a open loop control system, versus a closed loop system, right? So what we have here, if you, for example, for some weird reason, can't feel the temperature on your body, right? If you don't have a sensor, so right now our skin can detect the temperature, right? We have an inbuilt sensor in our body that can detect whether something is too cold or too hot, right? But imagine for some weird reason you didn't, right? Imagine you were completely numb, right? And you were just blindly controlling these, right? So that you kind of try to adjust the temperature without any sort of sensing of this temperature, that is called an open loop system, right? But in the real world, what we have is more of a closed loop system. So what we usually do is while we are controlling these inputs, we are constantly looking at the output, right? Like for example, when you're in the shower, you kind of keep your hand and you adjust your hot water and your cold water so that the temperature is adjusted to some sort of level that you want it to be, right? So you're constantly sensing the output, right? So you have a sensor sensing the output, right? So in a situation where you actually have a sensor kind of looking at the output, we say it's a closed loop system, right? So that's the difference between an open loop system and a closed loop system. So in an open loop system, we are just completely guessing, right? Without any sort of sensing. So we are just kind of arbitrarily changing these, hoping that the output will end up the output that we want, right? But in a closed loop system, we have some sort of sensor that is directly checking the output, right? That can kind of adjust the input in a way that we get the desired output, right? So that's really the difference between an open loop and closed loop system. So any questions regarding this idea? Nope. All right. So that's the basic idea behind systems and open loop systems versus closed loop control systems, right? So now let's think a little bit about how we can model these kind of systems, right? So obviously, if it's a case of so in this case, the person who is controlling this is you, right? There's a person here controlling it, right? So this is not automatic control. This is just control by a human being, right? So really where automatic control comes is this person is replaced by some sort of machine, right? A computer that will do this. So a simple control system like this is your ACs, right? Your air conditioning. So how the air conditioning works is you have so this air conditioning is an example of a automatic control system. So you have your air conditioner, right? And you set the temperature you want. You say, I want a temperature of say 20 Celsius, right? So you give it some sort of reference information saying this is what we want. And what happens is the air conditioner has a temperature sensor, right? Which will measure the temperature of the room. So the room temperature is your output. And then what it will do is it will compare it with this input temperature of 20 Celsius, right? And there will be an error between it. So for example, let's say the room temperature is actually 30 Celsius. But you said, okay, please give me 20 Celsius. So it will compare these two values and say that I need to cool this some more, right? So you'll have a system that blows air more depending on this error between the actual room temperature and the input temperature that you gave it, right? So that is an example of an automatic control system. So for all of this to work, we need to mathematically understand how to model systems, right? So that's what we're going to do next. So if you guys go to the PDF I gave you, right, you can see a simple mass spring system, right? So you have a spring attached to a block on the table, right? Actually, I'll use the notes itself to show you guys. Is my screen still showing the paint, or is it showing the PDF right now?
The paint.
Okay.
The paint.
Okay, hold on. Give me a sec. Now it's all right, right?
Okay, yes.
Okay. So we are going to look at how we can mathematically model a system. So I want you guys to go to page 6, right? So we have what we call a mass spring damper system, right? So we have a spring here that is attached to this mass, and then we have a damper that slows the mass down, right? You can think of the damping effect as something like friction or something like that, right? But we are imagine this is in a completely frictionless environment, and we are representing those damping forces by this damper, right? So the spring stores energy, the damper dissipates energy, right? So let's say basically these are the parameters that are associated with your system, right? You have force, you have a spring constant that defines the relationship between this force, the spring, and some sort of state that we are interested in, right? So there is a terminology that is super important here, and that is this idea of states, right? So hold on, let me take two. All right, so a state is basically, right, some sort of parameter that defines the system that we are interested in, right? So here, let's say we are interested in the displacement of this mass, right? That is how far it goes from its equilibrium point. So when we just leave the system, it will have some sort of equilibrium, and we are measuring how far it will go away from this equilibrium, right? Another state that will define this system is its velocity, right? How fast the system is going. And then, for example, its acceleration, right? That is velocity differentiated with respect to time, right? So all of these are typically things that we'd be interested in a system, right? It's sort of internal states that represent the variables in the system that we're interested in, right? So what the states are typically in a system is completely up to you, right? What are the states that you're interested in depends on the system you're looking at, right? So for example, in a previous example of air conditioning, for example, or the shower, right? The state that we are interested in is the temperature, right? And other states that we are also interested in are things like the angle of the tap, for example, how much we've opened the tap or how much we haven't opened the tap, right? So those are all the variables that we are interested in. So those are what we call the states, right? So there are different ways of mathematically modeling this system, right? And the most common and most straightforward way is what we call the state space model, right? And that's what we're going to learn, and that's what we are going to use. But keep in mind there are different representations of these models, right? There's another one called a transfer function, right? So you might have learned about transfer functions as well, right? But we are really going to consider state space models, right? Not transfer functions. We're going to look at these systems as state space models, right? So I'm going to explain what a state space model is, but before that, some of the advantages of using a state space model is given here, right? So it's very easy to derive a state space model because it directly comes from the physics of the system, right? So Yingshu, since you're interested in physics, this will actually be pretty straightforward. We're actually using physics which describe the relationship between physical things such as forces and these states to kind of model it, right? It's also good when you're dealing with multivariable cases. That means if you're dealing with states, like multiple states, for example, in our shower example, like I said, we care about how much the tap has opened, right? That's one state. And then we care about the temperature, that's another state. So we have multiple states, right? And using a state space model helps us model cases with multiple variables. And it's also suitable to study nonlinear systems, right? While as transfer functions only deal with linear systems. Okay. Anyways, coming back to how to derive a state space model. So we start with the physics, right? So what are the equations we know here from physics, right? We know that the oscillatory force that's associated with this is equal to minus kx, right? So that's Hooke's law, right? Hooke's law. That describes the relationship of the force applied to a spring and the spring constant and the displacement, damping is generally related to the velocity, right? So the higher the velocity associated here, the more the damping, right? So the damping force, so this is the force associated with the spring, this is the force associated with the damper, is generally equal to minus C into V. C is some sort of damping constant, right? So it's called the damping coefficient, right? So the relationship there is minus C x dot. So x dot is the velocity, right? You guys are following me so far, right? This is like high school physics. Anyways, so now we have a relationship between the force associated with the spring and then the force associated with the damper, and then we have an input force as well, right? So we have three forces, one associated with the spring, the damper, and the input force. So imagine the input force as someone may be pushing this, right, from externally. All right, so if you apply Newton's second law, that is F equals ma, right? How would you write that? Basically, you would say that your external force, right, minus your spring damper force minus your spring force and your damper force will be equal to mass into acceleration, right? So acceleration is actually x double dot, right? So this is your relationship using Newton's second law, right? What Newton's second law says is that the external unbalanced force applying on a system is equal to mass into acceleration, right? So the external unbalanced force is basically this. You have an input force coming here, you have an output force here, and you have this F force coming in, and you have the spring force acting this way and the damper force acting this way, right? By the way, imagine x is measured in the positive direction this way, right? Actually, yeah, if x is measured this way, x is,
Then after you apply force, it will become minus one.
yeah, actually, yeah, x will have to be measured this way.
Yeah.
Sorry about that. All right. Anyway, so you have this relationship. If you substitute these values, minus kx and cx and whatever, what you get is this relationship, right? Yeah. Okay, these pluses and minuses are slightly confusing. Sorry about that. Yeah, so actually what has been done is I've actually measured x this way, because if I subject f here, what I get is mx double dot, and minus fs plus fs will be minus kx and minus cx dot. But then if x is minus, this will become plus. Right? Anyway, it really depends on how you're measuring x, right? So let's go with this equation, right? And if I subject x double dot, we get this relationship, right? Yeah, so x has been measured this way as plus, right? Which is why when I substitute these values, it has become plus here. Okay. Anyway, you can double check that while rereading this. But yeah, so this is the relationship that you get between the acceleration and all the other parameters, right? Okay, so what you can do then is you can define what you call your state vector, right? So I'm going to define my state vector as these two values, your displacement and your velocity, right? And this is what we generally call a state space model, And it's when you take these equations and put it into this form, right? So here you have the state vector, here you usually have the input, and this equation describes the output. Okay, so how do we take this equation that we just derived using physics and put it into this state space form, right? So first you need to define your state vector, right? So the parameters that we're interested here is x and x dot, right? That is the displacement and its velocity. So if I have this x and x dot, right, how do these parameters relate to each other? So if you look at the state space model, you can see what you're relating is this state vector x with its derivative x dot, right? So if our state vector is x and x dot, what is our capital X dot? It will be x dot and x double dot, right? So what's the relationship between these two parameters, these two vectors? If you think about it, right, how is x and x dot related to each other? Okay, so if you think about it, right?
First derivative.
Yes, right? So it's the first derivative. If I try to put it into matrix form, right, these two vectors, right, you can see that if I put a 0 and 1 here, I will get x dot, right? So this state vector is related to its first derivative, right? Remember the difference between simple x and capital X, right? So capital X represents this whole vector, right? So I'm dealing with capital X here, right? So capital X and capital X dot and capital X, how it's related is like this, right? If I multiply x into 0, I'll get 0. If I multiply x dot into 1, I'll get x dot, right? And then the relationship between x double dot and the state vector is like this, right? And I need to also add right? So x into minus km is this term, and then x dot into minus cm is this term, plus f into 1 over m is this term, right? So I get this x double dot term here as well, right? So if the whole idea of the state space model is to show the dynamics of the system, that is how the system is changing, right, with the state vector as well as the input, right? So you kind of decouple the input and the state vector and showed how it affects the future, right? The future dynamics of the system, right? And you have to put it all into matrix form, like this, right? So to do that, this A matrix will have to look like this, and the B matrix will have to look like this, right? Is that confusing, the way I explained it?
No. Keep going.
Is that all right? I'm worried if I was a little bit confusing.
No, that's fine.
It's all right?
Yeah.
Yeah, so basically the whole idea of the state space model is it needs to ultimately look like this, right? So what this says is you're relating your state, those are the variables that you're interested in, with how those states are changing, right? So x dot gives you the dynamics of how those variables are changing, right? And you have to relate it to each other using this A matrix, right? And obviously not only does your states matter, your input also matters, right? So this section gives you information about the input. This section gives you information about the internal parameters of the system. So if you look at the A matrix and the B matrix, you can see that the A matrix has all these parameters that are related to the system, right? And C, right? These are all related to the system, internal parameters of the system. While as this BF term, the F gives you information about the external influence on the system, right? And then Y equals Cx tells you the output, right? So in this case, Y equals Cx, C capital X, right? So again, this depends on what you consider as the output, right? So if you're interested in the displacement as the output, right, your C matrix will look like this, right? Because X is equal to X and X dot, right? If you're interested in the velocity, your C matrix will look like this, and it will give you the output of the velocity. Cool. So this C matrix in your state space model really depends on what you consider as the output out of the states that you're thinking about, right? So this state space model describes the whole system, right? It describes how the dynamics of your states are affected by the internal parameters of your system and how it's affected by the output of your system. Sorry, the input of your system. And then it tells you about the output as well, how your output is related to the states. Okay, any questions before we move forward, because it's important to understand the state space model. So how you usually get the state space model is through some sort of derivation, mathematical derivation of your system, right? So that system could be it could be anything. It could be an economic system, it could be like a biological system or whatever, right? So you're ultimately always dealing with derivatives, because the derivatives give you the dynamics of the system. That is how that system is changing with time, right? Because in the real world, we are constantly dealing with systems that are changing with time. Whether it's an economic system or a robot, it's constantly getting affected by time, right? Its states are changing with time, and these equations need to capture all the information that gives you the relationships of the system, the input, as well as the state variables you're interested in, right? So system modeling is a whole other field, right? So system modeling is basically this process that we did, right? We use physics to come up with a relationship between all the parameters, and then we came up with the state space model, right? So system modeling is a field in itself and is quite complicated. So this is a simple example of like a mass spring damper system, but depending on your system, it can get even more complicated, right? So ultimately, you end up with this relationship here, the state space model. Yep.
So for each system, this model will be different.
Yeah. So this A matrix and the B matrix and the C matrix will be different, right?
No, like what I mean is this. Okay, A matrix and B and C will be different, but the structure, like AX plus BX, that will be same.
Yeah, that will be same. So this structure is what we call the state space model, right? So this is basically what we do is we convert. So what is this? This is a differential equation, right?
Yeah.
It's a differential equation,
Okay.
right? So a differential equation, and what we do is we convert the differential equation into this state space model. So this will change from system to system, right? What the dynamics of the system are, right? But what we do is we try to convert it into a common format, right? So think of the state space model as just a format, right? And it's a pretty convenient format because it nicely divides everything, right? It tells you that this term gives you information about the input, this term gives you information about the internal parameters of the system, this term gives you information about the output, right? So what we can do by creating a format, once we create this format, we can learn about how to manipulate this format, right? Without worrying about the underlying system, we can learn about the maths of this format, like what we can do with this format. And then what happens is when you're dealing with the actual real world situation, you model it into this format. And once you model it into this format, we know what to do because we've learned what to do with this format. Does that make sense?
Yeah.
Okay, so the state space model is just putting it into this format. Just like state space model, like I said, there's another representation which is called a transfer function, right? So what you do in a transfer function very quickly is you take this system and have you heard of Laplace transforms?
Yeah. But in the state space thing, you don't do Laplace transform.
You don't, right? So in state space, you don't do a Laplace transform. You just try to put these dynamics in a relationship with these matrices, right? So in a transfer function, you do a Laplace transform, and then kind of convert this differential equation into what we call a transfer function, right? So the reason why we do this is dealing with differential equations is a bit difficult, right? Because you have to solve these differential equations and and it's really difficult to kind of understand the relationships sometimes in differential equation. So we put it into these different formats, or actually a better word is representations, right? So one of those representations is state space model, and another is the transfer function. And in a transfer function, you just apply a Laplace transform to this, and it really makes the maths very easy, right? But one of the issues with the transfer function is you need what we call linear time invariant systems, LTI systems. Maybe you've heard of them, right? But don't worry about any of that. So transfer function representation, there's a lot to learn there as well, but we'll really be focusing on the state space model. And the reason for that is basically these three reasons that are given in this document, right? But just keep in mind there are different representations and ways of looking at the same problem. All right.
What is capital X dot means?
Capital X dot means...
It's just a symbol or something else?
No. Capital X dot is the derivative of this, right? So your state vector is capital X, right? If you differentiate capital X, that is X dot, what do you get? If you differentiate X with respect to time, you get X dot.
I get X dot, X dot.
Yes, exactly. Right? So what does that mean? That's just saying that, okay, this is how X is changing with time. And this is X. So what's the relationship between your current state and how it's changing with time? Right? And that's important, right? Like how you characterize a system is how it's changing with time. You need to capture that dynamics, right? Basically how it's changing. So this term is how it captures that, right? And the relationship between its internal current state and how it's changing with time is given by this equation, right? And that's the same pretty much here as well, right? Like that's what a differential equation gives you, right? How all these things are changing with time.
Okay.
Right. So this will give you the current state at present time and how that affects how it's going to change in the future, pretty much. Cool?
Okay, cool.
All right. So now we have a mathematical representation of a state space, right? So now what we're going to do is discuss. By the way, if you guys can just write these down. But again, everything is here in the notes, so it shouldn't be too much of an issue. I guess the stuff I draw on this paint stuff, maybe write them down. Okay, so now we have a mathematical representation of a system. So how that looks like is this, right? We have x dot equals ax plus b, hold on, let me draw this properly. X dot equals ax plus, by the way, I'm going to name the input u, not f, okay, because that's usually the normal representation of input. The reason why it's f here is because we were dealing with a force, right? So we kind of carried that here, but the common generalized notation is u, so I'm just going to use u here, right? And then you have the output, y equals c x, right? So what that means is you have the output coming here, right, and some sort of input u coming here, right? So now we'll learn how to do control on this, right? And the first, so there are different types of control techniques, right? So control techniques, closed loop control techniques, right? So we're going to talk about closed loop control techniques. Right? That is, you have some sort of feedback coming from the system, right? So there are multiple ways of doing this. So first we're going to learn about pole placement. And then we're going to learn about something called LQR control, right? Linear quadratic control. And then next week we're going to learn about PID control, right? So you might have heard these words before, and I'll be covering each of these. So this week I'm going to talk about these two, right? What is pole placement and what is LQR? Okay, so pole placement is basically where we don't really take the output, we take the states itself, right? That is x, right? And we feed it back. Actually, before jumping into that, before jumping into pole placement, sorry, we need to discuss about stability of a system. Okay, I'll come to control in a bit, but I'm just going to talk about stability a bit because pole placement will be more clearer when we talk about stability. So the stability of a system basically means that your output, it determines whether your output is bounded or not, right? So what that means is, let's say your final output when you put in an input grows like this uncontrollably, then you say the system is unstable, right? If it comes down to some sort of equilibrium, then we say it's stable, right? So let me discuss how to check whether the system is stable or not, right? So when you have a system in the state space model like this, can one of you tell me out of these information here, which matrix do you think will determine the stability of the system? Any ideas? Okay, cool. So if you think about it, okay, what does A matrix give you? The A matrix gives you the internal parameters of the system, right? So okay, what I mean by stable system or non-stable system is, think about a simple example. Let's say you have a table, right? And you place a glass cup like this right in the corner, right? So if I, for example, put a little bit of force here, it will uncontrollably go and just crash and break, right? But let's say I attached a spring or something to this glass, and now I apply a force, it will just oscillate, right? So basically the stability of the system really depends on the system setup, right? How is the system set up, right? So it's the A matrix that tells you all that information, right? What is contained internally in the system, right? So yeah.
But won't it even depend on the external factor?
Okay, so it's more like assuming you apply external force, will the system be stable or not, is the question, right? So
Yeah. Okay.
yeah, so for example, a pendulum or something, right? If you have a pendulum, right, it's, if you have it like this, it's pretty stable, right? As in, you swing it, it will come back and settle. But if you had the pendulum stuck like this, that's not in a very stable position, right? Actually, sorry, that's a wrong example, right? This will eventually come to some sort of stability. But there are some systems where it can't come to any sort of stable equilibrium. If you give it a bit of a force, it will go out of control, right? So those are uncontrollable systems, right? So how you really determine how this system performs is by looking at the internal parameters of the system, right? Whether it's going to be stable, whether it's going to be, for example, in a pendulum. What happens in a pendulum, for example? You have it like this, right? And you swing it. It's going to go like this, like this, like this, and then it's eventually going to come to 0, right? So if you think about the output, what will it look like? It will look like that, right? Imagine the output is the displacement from the center. It will look kind of like this, and it will eventually come to 0, right? So here it will have some sort of sinusoidal kind of behavior, right? So what determines this behavior of the output? It will be the internal parameters of the system, right? How long this length is, what is the mass of this system, and all that stuff, right? That will really determine its response to an input, right? Like basically how its output will behave really depends on what the system looks like. So all that information is typically contained in this A matrix, right? So I won't go into super detail about how the relationship between this and what I'm going to explain that much, but it has something to do with differential equations and solutions to differential equations. But if you take the eigenvectors of this A matrix, it tells you how the system will perform. Okay, now the reason for that is a bit more complicated, but I'll just give you guys an intuition for it, right? So I'm hoping all of you all have done differential equations before, right? So usually the solution for a differential equation like this, right, is basically x equals c to the power e lambda t or something like that, right? That is the solution to a differential equation, right? So this is what we call a time constant, right? So the eigenvectors of this A matrix typically relate to this exponential's time constant. So depending on this time constant, your output will change. right? So for example, if this time constant is positive, right, your output will grow like this exponentially, right, and your system will be unstable, right? If your time constant is negative, what will the output look like? It will go down, right? If your time constant is a complex number, right, that is something like this, a plus bj or something like that, or bi, sorry, complex number, what you will have is an oscillation, right? So you don't have to worry about this differential equation angle. Just remember, at like for this mechatronics course, all you need to remember is the eigenvalues, right? Sorry, not eigenvectors, eigenvalues of your A matrix tells you how the system is going to perform, whether it's going to grow unstably, decrease, or whether it's going to oscillate, or somewhere in between, right? Oscillates and goes down, or oscillates and goes up, right? And the reason behind that is because those eigenvalues are related to your differential equation solutions exponential time constant. Okay, so again, behind all of that, there's like I said, control theory, there's a lot of math and a lot of things to really understand underneath, and we don't have time, or like this is not a controls class in the sense that usually you would need an entire course to cover control theory, so I'm trying to do it in like 2 days, this week and next week, but for your robotics applications you don't need to go into super detail. You just need to understand the basics of a state space representation and basically how to check the stability, whether it's stable or not, right? So to check the stability, you need to check the eigenvalues of this A matrix, right? And what you need to remember is this: if your eigenvalues, right? Imagine this is the imaginary and real plane, right? If your eigenvectors are negative and real, right? If your eigenvectors are negative and real, then you have something like this, something going down, right? If your eigenvectors are the real component, okay, we are only looking at the real component now, that is along this line. If your real components are positive, right, if your eigenvalues are positive, you're going to have a situation of uncontrollable exponential growth, right, like the coronavirus, right, that is e to the power positive, right, and that's going to be unstable, and this is stable, right? And if you're talking about the imaginary, like let's say you have a purely imaginary eigenvectors, right, that is anywhere on this line, right, then you'll have a perfectly oscillating system. And then if your eigenvalues are somewhere in between, let's say it has a negative real component and a positive imaginary component, it's going to oscillate but go down, right? But if it's on this side, it's going to oscillate and grow, right? So if your real components of your eigenvectors, right, if your real components of your eigenvalues lie on, sorry, not don't say lie, are positive, system is unstable. If it's negative, it's stable, right? That's all you have to remember, right? So what you need to remember is if you have your state space model and you obtain the eigenvalues of your A matrix, and if they are negative, it will be stable. If they are positive, it will be unstable, right? And the reason behind this again is related to the differential equation solution, where your eigenvalues will end up as the exponential time constant, right? But again, you don't have to worry about the differential equation part. Just at this level, if you just can remember this fact, it'll be great. If you're naturally curious and you want to learn more, I suggest getting a nice control textbook and reading through it. It's not that complicated either, but we just don't have the time to go into solutions of differential equations and stuff to really cover all of that stuff, right? But this is the important takeaway that you need to remember. If you have your eigenvalues in the positive side, you basically have an unstable system. If you have it in the negative side, you have a stable system. Okay, any questions? Okay, good. So basically the idea behind pole placement is you look at your current poles, right? So what you mean by a pole are these eigenvalues. So in control theory, these eigenvalues are referred to as your poles, right? So what you do is you take a system, you look at its poles, you look at its eigenvalues, right? And if they are unstable, you can place those poles through control to achieve a sense of stability. Not just stability, any sort of performance that you want, right? For example, if you want it to oscillate, you can place the poles in a way that you place the poles somewhere around here, it will oscillate, right? And how much it oscillates also depends on where you place the poles, right? So basically, the entire performance of your system can be controlled using these eigenvalues, right? And how that system's output performs, right? So now we'll discuss pole placement. Before that, any questions about this eigenvalue stuff? Do you guys remember what eigenvalues are and how to get them?
Kind of forgot, but
Okay, I'll just cover a bit about eigenvalues again.
okay.
Yeah, I won't go again into super detail. And also, luckily, there's just a MATLAB function that just when you give a matrix, it gives you the eigenvalues, right? But okay, did you guys understand that basically the A matrix will tell you how your system is going to perform, and
Yes.
that parameters comes from the eigenvalues? That's what you need to remember now,
Okay.
right?
So basically, you find out A matrix eigenvalue,
Yep.
and based on the eigenvalue, you determine whether the system is stable or unstable.
Yes, correct.
Okay, this is the forward part. What about the back? Like, if you want to go backward, if you want to make the system
Yes,
stable, can we go backwards? Like,
exactly. So that's exactly what pole placement is,
oh, okay.
right? We design the system in a way where we can control where the poles end up, right? So now we're going to discuss pole placement. So imagine we have a system. Sorry. Right. So what we do in pole placement is we take a state vector, right? So this actually assumes that we can observe our state vectors. Assumes we can observe our state vectors, right? So usually this is some systems you can't observe it, but most systems you can. By putting a sensor or something, you can measure the state vector, right? You can measure, for example, in the mass spring damper system, you have some sort of system to measure its velocity and its displacement, right? So we have to make that assumption in this, that you can always measure it, right? So what we do is we multiply it by a gain matrix. That is just we multiply this into this, right? And what we do then is
is that gain matrix minus x or is it
minus k. Let me write that properly. Minus k, right?
Why is it negative, by the way?
So this is called negative feedback, right? So again, you can do it as positive feedback also, but generally the way we do it is using what we call negative feedback. Again, the equations will just differ with the negative and positive if you take positive feedback, right? But generally the standard is we take negative feedback because it's easier to create what we call the error term here, right? So the error is basically, let's say you have a reference signal. So this is the signal that you want the output to follow, right? So you say, I want the output to be, your reference, actually in this case, think of this as the input, right? So we have the input coming in here. And what we do is we take this minus kx and we feed it as the input, right? So what happens then is if you look at the equations, right? So before we have the input connected, you have u, right? So you have x dot equals ax plus bu. What we are doing is basically in pole placement. Actually, let's call it, If you're doing a pole placement, what you're basically saying is that u is equal to minus kx. That is, you're connecting this with this, right? So what happens to the equations then is x dot equals ax plus u becomes b into minus kx, right? So then right, and then what you get is x dot equals minus equals a minus bk into x, right? So what you've essentially done now is you've kind of changed. Actually, I've put a reference signal as well. Okay, so okay, let me do this again actually with a reference. Sorry about that. Okay, so if you don't look at the negative feedback part, this is what the system usually looks like, right? So how we apply negative feedback is we sample the state like this, right? And what we do is we add our reference signal and we add this into the system. So our new input is actually equal to, I'll call, instead of reference, I'll call this R, right? Is equal to minus kx plus R, right? So R is typically the reference value that you want the system to follow. For example, if you are talking about AC, let's say you want to set the temperature at 20 Celsius, right? So you would say, I want it at 20 Celsius. And what you're doing here is you're comparing it with the state, right? And checking whether, think about a better example. Yeah, okay. So in this case, your state also has your output, right? Like for example, in this case, what was the output here in this mass spring damper example? It was x dot, the velocity, right? Actually, if c is equal to 1 0, y equals cx, right? If c is equal to 1 0,
Output will be displacement.
output will just be x, right? So your state is part of your output. Sorry, your output is part of your state vector, right? Obviously, like you're always measuring something that you're interested in, right? So what you do here in this case is, right, you would have the reference value that you have, and then you look at how it is relative to, this is why you say negative feedback, right? You subtract it from your reference signal, and then you know how much of a difference between the actual value and the reference value that you have, and you feed that into this system, right? So let's just look at how the math works out, right? So you have x dot ax plus b into, so u has now been replaced by this, minus kx plus r, right? And typically you also put a gain matrix here as well, which I will call K2, or let's call it J. Remember, gain matrix is just a multiplication by some sort of value, right? So I'll just add that J just to scale that value up, and I'll explain why you have to scale up the input as well, right? So I'll just call this J, right? So what you do is, the important part in pole placement is this K, right? So what you've done is you've changed the input to be equal to minus kx plus jr, right? And then what happens is, you can see here that this becomes minus bkx plus bjr, right? And then if I factorize this, this becomes plus bjr. So what does this mean, right? What does this look like? This now looks like a new system, right? With x dot, this looks like your A matrix into x, plus this looks like your new input matrix. Does that make sense? Right? I won't call this A, this be like A dash, right? So what you've done is, by adding this negative feedback and this reference value, you changed your input into this format, right? And what you've done essentially when you do the math is you created a new system, right? So the new system, actually this is equivalent to a single system that has x dot equals A dash. So JR is, I'll call this U dash, right? Plus B into U dash with Y equals CX. Cool. So what you've done is you've created a new system pretty much by adding this is equivalent to this, right? So mathematically, when you kind of solve it, you can get the state space format again, right? So what that means is this K matrix is now affecting your new A matrix. Is that clear? Or do you want me to re-explain it, because I think I might have been a bit confusing? Guys, did I lose you through it?
No. It's kind of understood. Like basically, it's after the first loop, for example.
Yeah.
You update the input as well as the A matrix to readjust the output. Is it something like that?
Okay. Shall I quickly re-explain it? Because I think I did a bad job explaining it. Yeah. Okay. So you have a open loop system, right? That you want to control. So what is an open loop system? It looks like this. You have an output. Sorry, you have your state space model. Like this, right? So this is an open loop system. Now what is our objective in pole placement? We want to create a so what pole placement does is create a closed loop system where we get to decide where the poles are.
So basically, this pole placement is to stabilize the system.
Yes, to either stabilize the system or to kind of make it perform in a way that we want. Basically, it's a way for us to place these poles where we want, right? So, for example, if you take a system like this, right? We basically the poles of this system, that is the eigenvalues of your A matrix, are completely determined by the system, right? But we want to add a controller somewhere, some sort of control system here, right? That will kind of change this system in a way where now the new poles of this system is somewhere we want it to be, right? Either, for example, if it was unstable, we get to make it stable, right? Let's say we want it to be stable and oscillate, then we can place the poles here. Basically, we want control to where we want to place the poles, rather than being at the mercy of the system, right? So the idea is, how do we alter this open loop system, create a closed loop system, so that we can affect this A matrix, is the question, right? So how we do that is through creating a closed loop system, right? So how we adjust this open loop system. So this is an open loop system, and now we're going to create a closed loop system where we have more control over the dynamics of the system, right? So we have x dot equals ax plus bu, y equals cx. So what we do to exert a sense of control over the system, and for example, if we want to make it stable or make it oscillate, even if we want to make it unstable for some reason, right? What we do is we take its state, right? And we multiply it by this K matrix, and we add it, we change the input as well. So our input is something we provide, right? So we can change it so that we have another matrix here called J. We add these two values, and our input now becomes the addition of these two values, right? So basically this is what pole placement is. Pole placement is setting your input to equal minus k into your states. So you measure the states somehow plus j into some sort of reference value. So this is what pole placement does, right? This is what we call a control law. So this is where the control takes place. So we readjust. So this is what the system used to look like. It's an open loop system. We readjust the system such that our input to the system becomes minus kx plus jr. What does that do to the system? So what that does to the system is, if you just write out these equations, now u is actually this. So I substitute u by minus kx plus jr. So what that does is gives you a new system, right? So this is in the same format, right? This is in the same format of an open loop system. Where jr is your input, new input, right? So what we've essentially done is we've converted this system into kind of a new, okay, we've added feedback, but this is equivalent to a new open loop system with a matrix that is equal to A dash. Right? Why is this significant? Because these values, this j and k gain matrices, we get to set it, right? We've added these things ourselves, right? So by setting these k values to any value that we want, we can now affect our new system's A matrix. Is that clearer?
Yeah.
Okay, so we'll do an example and it'll be way more clear, right? So to do the example, we'll do exercise 1 of our tutorial, and it will be much more clearer if you still find it a bit confusing, right? So download your lab 4 week 5 questions, and we'll do question number 1, right? So we have a state space model. Since we're running out of time, I'll do it with you, right? So it says here we have a state space model with a A matrix minus 3 0 0 1 and B matrix 0 1, right? So this is question 1. We have A matrix equal to minus 3 0 0 1. Minus 3 0 0 1. So question 1 you have to do by hand, right? B is equal to 0 1. B is equal to 0 1. Okay. So what we have is an open loop system first, right? Which looks like this. Okay, and the first question is compute the eigenvalues of A and check if the system is stable, right? So in this question what we're going to do is we're going to do pole placement so that the system becomes stable. right? So question 1, right? So the first part of the question is find the eigenvalues of A. So how do you find the eigenvalues of A? Basically, you need to use this equation. So again, I won't go into detail about eigenvalues. I'm pretty sure all of you have done it in your undergrad, and if you don't remember after this class, just do a bit of refreshing. But basically, how to find the eigenvalues is you say determinant lambda I minus A equals 0, right? This is how you find the eigenvalues of A. Right, so eigenvalues are these lambda values. I is your identity matrix. Most of you might be able to remember when you see this equation, but just remember this is how you have to find the eigenvalues. Again, in the next couple of exercises, you realize in MATLAB there's an easy function. When you just input this A matrix, it will give you the eigenvalues that you're looking for, right? But let's do this question by hand, so it will remind you how to find eigenvalues, right? So how you do this is find the determinant of lambda I minus A, right? So we have a determinant that is lambda into I is lambda into the identity matrix, which is lambda 0 0 lambda minus A. A is minus 3 0 0 1 equals 0, right? And what that means is determinant lambda plus 3 0 0 lambda minus 1 equals 0. And if I find the determinant of a 2 by 2 matrix, it's just this into this, right? Minus this into this. So that's lambda plus 3 lambda minus 1 minus 0 into 0, right? So that's lambda plus 3 lambda minus 1 equals 0. So you can see here, since it's a 2 by 2 matrix, you have a quadratic equation, which means your answers are going to be, you're going to have two lambda values. Lambda 1 equals 1 and lambda 2 equals minus 3. So these are your eigenvalues. Looking at these eigenvalues, is this system stable or unstable? Guys, is this system stable or unstable?
One part is like, since it's negative, it's stable, but the positive side.
Yeah, so having even one that's unstable will create instability, right? So this system is, so all the eigenvalues have to be negative for it to be stable. So this system is unstable, right? Was this clear about how to get eigenvalues? You just have to solve this equation, that's it. So you guys remember how to do determinants and stuff? So hope.
I just use the MATLAB function.
Okay, cool. These are the values you get, right?
Okay, yeah, minus 3 and
Okay, cool. So you can watch this video just to remember how to get the eigenvalues again. It's just this equation. So yeah, if you have even one value that's positive, you're going to have an unstable system, right? Shall I think maybe revise what I wrote here. If your real component of your eigenvalues are positive, system is unstable. If just mention here, all have to be negative. All eigenvalues have to be negative. Or you can use the word poles now, because we are dealing with control theory. Just use the word poles. All poles have to, poles or eigenvalues have to be negative. Okay, anyways, back to what I was talking about. Okay, so we have instability, right? So now what we're going to do is pole placement. So question 2, check the system controllability. Okay, so for pole placement to work, it has to be controllable, right? So that's one other thing I need to tell you about. So if you open the PDF notes, on page on page 20, it says here how to check for controllability. So controllability is basically this matrix. You need to create this matrix and check the rank of the matrix, right? So what I mean by that is, so it's b AB into a squared b into a to the power n minus 1 into b, right? So in the case of this example, the controllability matrix is a into b, right? So that's minus 3, 0. Actually, I'll do it in paint. B, AB, a squared b. Okay? So we need to check controllability, you need to calculate what you call the controllability matrix, which is b, a squared b, and so on, right? Depending on the size of your matrix. So what is our b vector? 0, 1.
0, 1.
Yeah. So that goes 0, 1. A squared b is going to be
9, 1.
Oops, sorry. Where is it? What is a squared? A squared is minus 3, 0, 0, 1 into minus 3, 0, 0, 1. So minus 3 into minus 3 is 9. 9 plus 0 into 0 is 0, so it's 9. 0, 0, 1, right? And that into, so this is a squared into b. B is 0, 1. 0 into 9 is 0. 0 plus 0 is 0 plus 0 into 1 is 0. 0 into 0 is 0. 1 into 1 is 1. So you get 0, 1. Uh, 0, 1. Is that right? Give me a sec. Minus 3, 1. Our B matrix is 0, 1, is it?
Yep. 0, 1.
Okay, so I need to make a small change to this question. So the question I given you, this matrix is not controllable. It's a small problem. Sorry about that. How did this happen? Actually, we can still do it. Okay, so this system is actually uncontrollable. So, okay, how you check that is you get this controllability matrix and you check the rank of this matrix, right? So, what the rank of a matrix is, you have to check how many rows of this matrix are linearly independent from each other. So, do you guys remember what linear independence is? It's basically, for example, if I had a matrix like this, right? This row is linearly independent from this row because you can't form this row from this row, right? Again, if I had a matrix like this, for example, again, these two are linearly independent from each other, right? But if I had a matrix like this, I can just multiply this row to obtain this row, right? Or divide this row to obtain this row. So the number of linearly independent rows here is 1. The number of linearly independent rows here is 2. Here it's also 2, right? So your rank is the number of linearly independent rows, right? So here it's 2, here it's 1, right? So if I had an example like this, again this is 2, rank 2, right? You can't change, you can't multiply this by anything to get this, right? So if your rank, that is the number of these linearly independent rows, matches the dimension of your matrix, then we say the system is full rank, right? So if your controllability matrix is full rank, then your system is controllable, right? Fully controllable. If it's not full rank, it's not controllable. So in this example, right, what is the rank of this system? It's 1. So this system is not controllable, right? So the answer to question number 2 is that it's not controllable, right? So for you to do completely arbitrary pole placement, that means to place it anywhere you want, it has to be controllable, right? But if it's not controllable, there are certain poles you can place it at still, right? But if it's, you can't place it everywhere you want. You can only place it in certain places. Okay, because one of these will be linearly dependent on the other. Okay, so this is not controllable, which means you cannot pole place anywhere you want. Only certain places, only certain poles, right? And that will be clearer in part 3, right, when we do the actual pole placement. Okay, so cool, is that clear? So that's what the controllability matrix does. Again, in MATLAB, there's an easy function to do that. You just use this function called CTRB. That will help you do check your controllability. Okay, so now we'll do question 3, which is the most important part. Is that clear about controllability matrix? Again, the notes I have given you should have some examples, right? 2 examples of a controllable matrix and a non-controllable matrix, right? Okay, so now we'll do question 3, which is perform pole placement to place the poles at -3, right? So what does that mean? That means, just to recap, we had an open loop system, but now we're going to create a closed loop system. So we're going to create a closed loop system like this, right? We're going to take multiplied by k and add it to a gain matrix times reference signal and feed that into it as our new input, right? So what are the equations you get when you do that again? You get x dot equals a minus bk into x plus b into j into r, right? So this becomes our new system matrix. So this is what the closed loop systems relationship looks like now, right? So the question in pole placement is, what is this k value? So pole placement is really about what is the k value, or what should k be for me to get my poles at, according to this question, we need to place the poles at -3, -4. At -3, -4. Right? So what should I do to get my poles? How should I design my controller so that I'll get my poles at -3, -4, right? So how do you do that? What you do is, now this is your new A matrix, right? So what you can do is you can put some variables to k, pretend like this is the new matrix, and find its eigenvalues, right? So what is the dimension of k? What will k look like? K will have to look like this, right? Because it has to be multiplied into b, and you need to be able to subtract it by a 2 by 2 matrix.
Okay.
Yeah? So what does A dash look like? A dash looks like this, right? A minus bk. A is, can someone tell me what A is again? 3, 0?
-3, 0, 0, 1.
0, 1, like this, right? And then you have B, which is 0, 1 into k.
K1, okay. So we do this part and equate it to -3,
Yes.
-4.
Yeah.
That's
So what you get as your new A matrix is going to be, so this into this is going to be k into this is 0, k2 into 1 is k2, and then this into this, yeah, sorry, it's 0, this into k2 is 0, 1 into k1, k2, that's what you get, right? So you have -3, 0, 0, 0, minus k1, 1 minus k2, right? So I've just solved this, right? And this is what I get. Now what you need to do is find the eigenvalues of A, right? So what is the eigenvalues of A? Determinant determinant lambda I minus A dash. Sorry, eigenvalues of A dash, which is equal to 0. So what does that mean? You have lambda 0, 0, lambda minus -3, 0 minus k 1 minus k2 equals 0, determinant, right? So you get lambda -3, 0 minus k, it should be k1, lambda plus k2 minus 1. By the way, just make sure I'm doing the math correctly. 0. And then to get the determinant, you multiply this into this, which is lambda minus 3 into lambda plus k2 minus 1, and then 0 into minus k1.
First case, lambda minus of minus 3 will become plus 3. So it's lambda
Okay,
plus 3.
thanks. Okay,
And the lambda,
everything else is alright.
yeah.
And then and this has to be equal to 0. So you get lambda 1 equals minus 3 and lambda 2 equals 1 minus k2. So what are the poles we need to place it at? We need to place the poles at, according to the question, at minus 3 and minus 4, right? At minus 3 and minus 4. So one of the poles are already at minus 3, right? So this is that issue with controllability that I said, right? Like, even if we had to pick, so I've actually crafted this question in a kind of a crafty way. For example, instead of minus 3, if I said I want 5 and minus 4, will I be able to control that? No, right? It will always be minus 3. There is no k term here that can affect this, right? But since we want it at minus 3, and all we want to do in this, right? If you remember the previous poles that we got, what were the poles that we got? We got 1 and minus 3. This is the guy who's causing the instability, right? Not the minus 3. So all we are trying to do with although this system is not controllable, fully controllable, we can still control this one, lambda 1, so that we can make this also negative somehow, right? So we don't really worry about this minus 3 because it's already in the negative side, right? All we have to do is try and affect this lambda 1, right? But remember, if a system is generally uncontrollable, you can't place all the poles that you want, right? So lucky for us in this question, one of the poles is already negative, and the one we want to control is the one here, right? So if we want to place the pole at minus 4, what should k2 be? You just substitute lambda 2 as minus 4, 1 minus k2. So k2 will be equal to 5. So what that means is, if I created a controller and if I fed back, if I had a sensor that is measuring my state inputs and fed back that state input with a gain matrix, all we have to do is multiply it by this matrix k1, k2, right? K will have to be equal to k1, 5, right? K1 doesn't matter, right? Because k1 doesn't really factor in the end, right? All that's ended up in our equations is k2, right? So it doesn't really matter what we set k1 to. K1 can be 2, 3, 4, 5, 6. It doesn't really affect the ultimate thing. But as long as we set k2 as 5, we will get our final poles in the place that we want. Is that clear?
Yep.
So that's what pole placement is, right? Basically, ultimately, this is what affects our final poles. I will explain why we have to scale this input later. So as you can see, that input scale doesn't really affect our question in pole placement right now, right? But the scale matters when we are trying to, so the pole placement that we did here finally was to make the system go from unstable to stable, right? But that's not the only thing that we usually want to do. We want the final steady state of your system to come to a certain value, and that is what's affected by J, but that will be clearer in the next question. But yeah, this should hopefully give you an idea of how pole placement works. It's basically figuring out these k values so that we get the poles that we want and the performance that we want, right? So that is question 1. Now, using all of this knowledge, now we did this entire question by hand, right? And you can see how annoying it is, and there's a lot of linear algebra and all that stuff. But MATLAB makes it super easy, where you can use a lot of easy functions to get what you want done, right? So we talked about the mass spring damper system. Can you try question 2 by yourself on MATLAB? And I will do it quickly after that. So I'll give you guys about 10 minutes to try it out. In the meantime, if there's any questions, please feel free to ask me.